Okay, so this question asks us to take a look at 1,2,4,5 tetramethylcyclohexane. Both of these structures are 1,2,4,5 tetramethylcyclohexane. We're going to figure out which one is going to have the lowest energy conformation. Remember, every cyclohexane has two different chair conformations, sometimes one of which is going to be higher energy or lower energy than the other. And so what we need to do is we need to examine all four possible chair conformations to decide actually which one is the lowest energy. Okay, so what we need to do and what you need to be able to do is learn how to draw the different chair conformations, including all the bonds. And so the way we do is we start out with two parallel lines that are slightly offset from each other. And then we connect them going down on that side and up on that side. Now we're going to swap it for the chair flip. We're going to do the same thing. We're going to start with two parallel lines, but we're going to face them in the other direction. They're still going to be offset though, because we want to come up on this side and down on that side. Now with the iPad, it's easy to rearrange and resize things so that they're relatively in the right position. You're going to have to kind of learn how to do this by hand. Now, the next thing you want to be able to do is you want to be able to draw the axial and equatorial bonds. You need to figure out a way to do it that's right. Some students will not draw the bonds at all, and I see this a lot. And about half the time that students don't draw the bonds, a little more than half, it's because they don't know what's going on. And learning how to draw the bonds is what teaches you what's going on. The other half, slightly less than half, students do know what's going on and they draw the right picture, so that's fine. If you know what's going on and you can draw the right picture without drawing all the rest of the bonds, and you want to save that 32 seconds, then by all means save the 32 seconds and don't draw the bonds. But I'm going to go ahead and draw them. And when you do draw them, we need to draw them consistently. We need to draw them consistently and correctly. And so the reason why I do it this way is because I don't have to think about it. It's just the same way every time. I always start with the top leftmost atom. And I start by drawing an up bond. So up, down, up, down, up, down. Now I'm going to draw the equatorial bonds. Down, up, down, up, down, up. Now, I'm going to mark this atom. The reason why I mark this atom is so that I remember which atom is the same in both chair flips. I want to mark this atom because in the right-hand chair structure, this is that atom has moved to the down position. And so I want to mark it just so that I know. Now, in order to be consistent, in order to figure out a way to draw bonds that are consistent, and I don't have to think about every time, I still start in the upper left-hand atom. Now, I'm using two different colors. And because I'm using two different colors, I have to make sure that I remember that what was an equatorial bond becomes an axial bond, and what was an axial bond becomes an equatorial. So I'm going to switch colors, but I'm still going to start at the top left, and I'm going to go up, down, up, down, up, down. Now I'm going to go equatorial, down, up, down, up, down, up. And of course, because I'm a iPad, I can just copy and paste it down there. And so now I've got my four frameworks worked out. Now, I'll just point out, let's take a look at this atom that's highlighted. The axial bond becomes the equatorial bond, and the equatorial bond becomes an axial bond. But they don't switch positions. If the bond was in the up position in one chair, it's going to be in the up position in the other chair. And so what students often get confused about is this idea that there are both two separate concepts. The concept of axial and equatorial, that's one concept. And the other concept is up and down. They're different, they're separate concepts. There are both up and down axial bonds. There are both up and down equatorial bonds. If a bond was up in the chair flip, it'll still be up. It's just not, it just goes from axial to equatorial or vice versa. Okay, so let's sort it out. So now I want to put the groups in the correct position. Remember, it doesn't matter where I start as long as I pick a place to start and then I'm consistent. So I'm going to go ahead and think about this. I'm going to say, all right, let's arbitrarily make that the atom that's highlighted. Okay, so that means that I have a CH3 group. And remember, I use a wedge towards me as I use that as arbitrarily meaning up. And it's fine as long as you're consistent, just pick one. And so that means I've got a hydrogen there. And so I'm going to go around. This time I'm going to go counterclockwise. And so I've got a CH3 group, the next atom over, and it's pointing in the opposite direction as the first CH3 group. Since I put the first CH3 group up, the second CH3 group goes down. So then I'm going to skip an atom, and then I've got another CH3 group. It's pointing in the same direction as the previous CH3 group. I'm going to go ahead and fill in some hydrogens while I'm at it. And then I'm going to continue to go around the circle counterclockwise. I've got a CH3 group. It's up now. It's opposite of the direction of the last one. So that means it's there. And so now this is where it comes in. This is where marking the actual atom comes in at, because then I know where to put the CH3 group. Now, because I'm using two different colors, I know it goes on the blue bond, no problem. But if I'm not using two different colors, then I know also that it was on an axial bond, so it needs to be on the equatorial bond. And I can also say to myself, it was pointing up and it's still going to be pointing up. So let's go ahead and finish that out. Now, in order to get it correct, I want to go counterclockwise around the ring. And so counterclockwise around the ring is this direction. And so the other one was pointing down. And so the CH3 group is pointing down. It went from axial to equatorial, but it's still pointing down. Okay, now let's continue to go around the ring. These were hydrogens. And then I've got a CH3 group. It was pointing down, so that goes there. And I'm going to continue to go around. This one was pointing up, so that goes there. Okay, so now I've got the two ring structures. I've got the two chair flips. And so let's do the next one, and then we'll examine for energy. So again, I'm going to arbitrarily start here. So this one was down, CH3. Going to go around the circle. It's pointing up. That's there. That's an H. Skip an atom. So there H's. Around the circle, it's pointing down. So that's this one. Going to go around the circle. It's pointing up. So that's this one. H, H, and H. So I've got all three of those groups. So again, making sure that I remember that it's this one and this one. It was pointing down. The CH3 group is still pointing down. It was equatorial. It's now axial. I'm going to continue to move around the circle counterclockwise. And so that's CH3 group was pointing up. It's still pointing up. It was equatorial. Now it's axial. Got to go around and skip an atom. So it was, let's see, where am I at? Skipping an, what did I just did? Okay, thank you. All right, so let's go around here. CH3, skip an atom. And now I'm here. There's my CH3 pointing down. Axial went to equatorial. And then now I've got CH3 pointing up. Axial went to equatorial. Okay, now that I've got all four structures written down, and I've got the equilibrium expression of the chair flips, I can examine which one is the lowest energy. So let's take a look. In this one, I have 1, 2 CH3s in an axial position. So I have 2 CH3s providing 1, 3 diaxial strain. In the chair flip, I have 1, 2 CH3s in the axial position. They provide 2 CH3s worth of 1, 3 diaxial strain. So it turns out that both chair conformations of this structure are actually the same energy. It turns out it's actually the same structure, but it's the same energy. Two instances of 1,3 diaxial strain. What about this one? 1, 2, 3, 4 instances of diaxial strain. And in this one, none of the axial bonds are the CH3 groups. They're all the CH3 groups in this case are in equatorial positions. So it turns out at the end of the day, this is the lowest energy chair conformation, which means that this is the lowest energy version of 1, 2, 4, 5 tetramethyl cyclohexane. Okay.